Hello, my name is Mauro DALLE LUCCA TOSI, and I'm here to present my research on convergence time analysis of asynchronous distributed artificial neural networks developed with Venu Venugopal and Martin Theobald at the University of Luxembourg. First, let me introduce neural networks training. A neural network can be represented by a weight matrix, and they are trained by mini batches of training data. Basically, the model is going to receive these mini batches input data, calculate a gradient based on it, and apply it to itself in order to improve for next iterations. The calculation of the gradient is the most time-consuming part of our computation, and the application is pretty straightforward. It's just a summation. This seems a very straightforward operation, but actually it is very time-consuming. Now, how can we reduce the time that it takes for us to train a neural network? We can use a distributed setting. In this research, we are presenting a convergence time analysis on an asynchronous distributed setting. And we are also formalizing the concept of staleness here, that I will introduce in a few moments. First, we have a mini-batch generator, generates a blue mini-batch, and sends it to be computed by model A. And meanwhile, model B and C, they can also start computing the respective mini-batches. After model A finishes computing the blue gradient, the blue reference to the blue mini-batch, it can apply it to itself. And here, in the application of the gradient, is the first time that we see the concept of staleness. Here we have a staleness of 0, that it is basically representing the difference between the model that calculated and applied this gradient. As the blue gradient was calculated and applied by the same model, the staleness is 0, because the difference between model A and model A at this exactly the same time is 0. And the same occurs for model B and C when applying the red and the green gradient. Now, it's interesting to note here that the model A can exactly after applying the blue gradient, send this gradient to the other models, but before receiving the gradients that the other models computed, it can start computing the yellow gradient. It does not wait for the other models because basically this is asynchronous, and this is why we need to be very careful with the staleness that we have. Now, after applying the respective gradients, model B and C, they can apply the gradients that they received from model A, the blue one. And here we have a staleness different from 0, 1, because as you may remember, the gradients applied to model A at the time that it calculated blue is an empty set because they have not applied a single gradient beforehand here. On the contrary, the model B, when it applied the blue gradient, it had already applied the green gradient to itself. Therefore, the sets equals to green. And the symmetric difference between these two sets represents the symmetric difference between those two models is 1. Therefore, the staleness of the blue gradient here is 1. And the same occurs for model C here. And this staleness can be different depending on the time that the gradients are applied on different models. And in the end, as you may see, all the gradients were applied to all the models. They were applied on different orders in each model, but they were applied to all the models. And as you will remember, the gradient application is just a summation, and as all the models sum the same values, you can expect that they are going to converge in the end. Okay, but this convergence is referencing here is among those models, model A, B, and C, right? But what happens for the convergence of the whole network? Is it going to converge to local minima or not? How can this staleness impact this convergence? Okay, so in our experiment, we evaluated a virtual VEC model training on Wikipedia using the TensorFlow C API and distributing this using R on an HPC scenario. In the first plot here, you can observe that we have 10 lines, which actually we can differentiate because they're exactly one over the other. So in reality, we have 5 lines here, continuous lines, and 5 dotted ones, representing the training and the evaluation using, the training and the test using from 1 to 16 nodes. But as the lines are exactly one over the other, it's a very good thing because it basically means that it doesn't matter the amount of nodes that we are using in this training, 1 or 16, and the loss curve continues exactly the same. So it's not impacted by the staleness that I previously introduced. Now, for the convergence time analysis, for the convergence time ratio, we have a very different result. Here in the second plot, we analyze the time that it takes for us to train one node divided by the time to train any nodes. And in black here, we have the ideal speed up. As you can see, when we use small mini batches, we can get pretty close to an ideal speed up. But when we use greater mini batches, this speed up is not as good as it was with smaller ones. We believe that this occurs because it takes much more time to train smaller networks with smaller mini batches than with greater ones. Therefore, the margin of speed up using smaller mini batches is much higher. Now, for future works, we're going to perform those experiments using different models, not just sparse ones as word2vec, but dense ones as well, and we're also going to train this using GPUs. Those are our references, acknowledgements, and thank you very much for your time.